Okay, for chapter 24, I only had one problem here for you to do. There's not going to be a lot in the line of problems for this chapter. You have to know about Maxwell's four equations and how Maxwell modified Ampere's law to add the displacement current, the equivalence of a changing electric field to a current. And then you have to know some basic things about electromagnetic waves. So this problem here is with those basic things about electromagnetic waves. So we'll start with reading the problem. An electromagnetic wave with a wavelength of 2.00 micrometers. Now remember, the symbol we use for wavelength is the Greek letter lambda. That's a lowercase l. 2.00 micrometers. It's traveling east through a vacuum. Vacuum means something important to us. Vacuum means that the velocity for the wave is equal to the speed of sound, 299792458 meters per second. That's a 5. And it tells us it's traveling east, so I'm putting an E with a, well, I'll put the word east, just to make sure we're clear. It's traveling east. So in my picture here, there's my direction for the velocity. At location x0 and time t0, the electric field is pointing north. And so I will put green here for my electric field. The electric field is pointing like that, which is why I put east there instead of just E. It has a magnitude of 6.44 newtons per meter. And I'll put here as well to make it so it's truly a vector. And, you know, I wrote out the full number there. I'll just put 2.998 times 10 to the 8th meters per second to make it easier to write. So that's what's given in the problem. Now, the first question is, what part of the electromagnetic spectrum is this wave in? Well, if you look in your textbook, you have the electromagnetic spectrum is given to you in section 24.3, and it has a figure there. The figure is right under equation 24.6. And in looking at the figure, it shows radio waves going from frequencies of around 10 to the 0 hertz, in other words, 1 hertz, up to around 10 to the 12 hertz. And then it subdivides that radio waves and says that AM radio is just a little bit above and below 10 to the 6th or a million hertz. FM radio is around 10 to the 8th hertz, and TV is going from a little below 10 to the 8th, so let's say somewhere in the ballpark 10 to the 7, up to somewhere around 10 to the 9 hertz. And then if you keep going, infrared starts at about 10 to the 10 hertz and goes up to the visible spectrum, which is in the 10 to the 14th range. Visible spectrum, as we talked about in class, goes from around 4 times 10 to the 14th hertz up to 7.5 times 10 to the 14th hertz. And then it goes further ultraviolet. It shows going from the end of the visible up to around 10 to the 18th hertz. X-rays going from about 10 to the 16th up to 10 to the 20th hertz, and gamma rays from about 10 to the 18th up to very high. Now, I did all of those in hertz. We're not given hertz, we're given wavelength in micrometers. So if we look at that same figure and look at the top, you see the wavelengths for the different spectra, and you see that a micrometer, that means 10 to the minus 6 meters, falls there really close to the visible spectrum, but below it clearly in the infrared range. So this has to be infrared by looking at that figure. So, and just to be clear, that figure says that infrared goes from about 3 centimeters to about 0.75 micrometers. And so 2 is definitely in that range, 2 micrometers. Second question, what is the frequency of this wave? So for part B, we're going to have to do a calculation. Now, what's the equation to use? Well, since we were just looking at that figure, equation 24.6, right above it, is the equation to use. Equation 24.6 says that the speed of the wave, c, is equal to the frequency times the wavelength. So if I want to solve that for frequency, frequency is equal to the speed of light over the wavelength. And so that's my, just using the 4 significant digits, 2.998 times 10 to the 8th meters per second. Notice I do not have a vector there. It's just the scalar. Divide by the wavelength, 2.00 times 10 to the minus 6th meters. And that gives me a frequency of, you can immediately say, well, that's going to be around 1.5. The actual number is 1.50 to 3 significant digits times 10 to the 14th hertz. Make sure we can read that as a 14. So let's put that in here. Now, what's the magnitude of the magnetic field at this instant and location? So notice I gave you an instant and a location there. And so how do I find this magnitude of the magnetic field? Well, now if we go back to section, I believe it's 24.2, section 24.2 gives us the relationship between the magnetic field strength and the electric field strength. It's in equation 24.3. And so equation 24.3 says that the electric field strength divided by the magnetic field strength at any instant is equal to the wave of the speed of the wave. So in this case, we want to solve for B. So B is equal to E over C. And so I take my electric field strength, which was 6.44 newtons per meter, divided by my speed of light, 2.998 times 10 to the 8th meters per second. And that gives me a magnetic field with a strength of 2.15. Okay, nice. Times 10 to the minus 8. Now, if you look at that, that's going to give me units of newtons seconds per meter squared, or Teslas. So there's my magnetic field, 2.15 times 10 to the minus 8. And finally, in what direction is the magnetic field pointing at this instant and location? Now, if you go back to section 24.3 in the textbook, it shows, I think it's 24.3. Uh-oh. No, it's 24.2 where I was. Or with some bad luck, it could be 24.1. So yeah, section 24.3 where I was there. You have a figure, figure 24.7 shows an electromagnetic wave with the direction of the electric field, magnetic field, and velocity. And the relationship of the directions there is immutable. It has to be that way. And if you look at that, in the figure, it has electric field like this, magnetic field like this, and velocity like this, so that they're all mutually perpendicular. In an electromagnetic wave, the magnetic field and the electric field are always mutually perpendicular to each other and to the velocity. And so this gives us a right-hand rule relationship. And so you could look at this and say, well, the direction of E crossed with the direction of B has to be the direction of V. But if you want to actually get the correct equation is that the electric field is equal to the magnetic field crossed with the velocity. This is the correct relation that gives you both the electric field strength and the direction of the electric field, if you know the magnetic field, and the velocity. Now, in this case, we've already used the scalar version of this equation. Notice if I take this and take the scalar value, since magnetic field is always perpendicular to the velocity, then taking the scalar, I'd have E equals BV, or E over B is equal to V, that equation. So you can see they're fundamentally the same equation because we have that right hand, well, the mutually perpendicular. So I'm just going to take this relationship and I'm going to go back up and look at my diagram. So writing out that equation up again up here so I can see it where I'm using it, I have electric field vector is equal to magnetic field vector cross the speed of the electromagnetic wave vector. So as always, with the right hand or with the cross product, the index finger is the first item in the cross product. The middle finger, which has to be bent at an angle away from the magnetic field in the direction that the middle finger will bend away from the index finger. In this case, they're perpendicular, so it's the direction your palm is pointing, is the velocity. And then the electric field is the answer, and the answer is the thumb. So I take my right hand, and I'm going to say, okay, I need to have my thumb pointing north. And I need to have my middle finger or my palm pointing east. So I take my right hand, orient so my thumb is pointing up, and so my palm is pointing east, and my index finger is pointing out of this. Now, in this diagram, this is a diagram north, south, east, west that has up as coming out. And so that's got to be the direction of the magnetic field to be consistent with this cross product. So now that we've determined that, let's double check just by pointing my index finger up out of the page, make my middle finger so it points to the east, my thumb then points north. So my direction is up. So here we use the right hand rule. And that's it for this problem. Short, sweet. Have a great night.